Okay. Today, let's go to start with binary trees. And binary trees, the representation for binary trees are something like that. For example, one, about the tree, I have one. Something like that. So tree, I have one, number 2, number 3, for example, something like that. Everyone's know about what means that binary trees or binary trees. Everyone's know about what that means. What is a binary tree in computer science or not?
No.
It's a way to represent information. It's similar to a tree. We call trees because have the shape of a natural tree. It's like something, you are branches, something like that. Here you can have another branches here. At the end, the representation of that is something similar to a natural tree. Well, here you put some elements, usually with the numbers or whatever.
What do you use it for?
We use that because it's a way to organize information, to do fast search. For example, if you want to find a number in a big set of numbers, one of the faster way to obtain this number is using binary trees.
Okay.
It's a theory about algorithms that say, okay, to try to find a number is the order of n. What means that? Is the order algorithm efficiency. What means? Usually we call OR, it's like an order. What means that? Or n, that means you need, if you have a data set of 1 million of data, you need think about to check if this number is inside this tree. You take 1 second. You need 1 second to check if the number is to compare the number you are looking for and then this number. Think about, you need 1 second for each operation. You need 1 second to each compare operation. Okay, so if you have n and n is equal to 1 million, so that means you need 1 million by 1 second. It's you need all this time to check if, in this case of you need 1 second, you need 1 million by 1 second of time. And let's go to take the calculator. 1 million seconds divided by 60, that are minutes, divided by 60, that are hours, divided by 24, that are days. You need 11 days, more or less. It's
Okay.
11 days to obtain the result. Okay, but if you need to do that search faster, you can use, for example, a binary tree, and the order or the efficiency of this algorithm will be logarithm of n. That means see, 1 million logarithmics. That means 6 seconds. If you have 1 million, you need only n equal 1 million. You need 6 seconds to obtain the results. So the difference in the same algorithm, or to search one number using this algorithm, you need 11 days, and with other algorithms using binary tree, you only need 6 seconds, more or less. Okay.
Okay.
So this is much faster. This type of structure are used, for example, to create index of databases, hashes, index and hashes in databases. Okay, because it's very fast to get a solution when you find a number using this structure of tree. Okay.
Yep.
Okay, nice. After this introduction about why use this binary tree, let's go to give the representation of this tree in Prolog. In Prolog, if we have a tree like this, for example, think about the usual tree we see in this way, but the user representation in computer science, we invert the tree. We make an inversion of the tree. It's like we have the root of the tree up, here is the root, and then we represent the other numbers, something like that. So usually we will see the representation of trees in this way. Okay, so we make an inversion of the tree. We don't represent in this way. It's more usual to find a representation in this way, with the root of the tree in the up side of the representation. Okay, so how to represent this tree in Prolog? Usually, let's go to write the more simple one. This one. Okay, let's go to represent this only with 3 numbers. We use the word t, or the predicate t, and then we have a label and right, left, tree, and right tree. This is the representation. So if we want to or the structure of this predicate t, so if we want to represent this tree, we will write t number 1, and to the left we have another tree, and represent like 2, and we have in trees we have an empty tree that we call nil. It's a way to represent and empty trees. Like here, there are no more songs in this node. This tree don't have more elements here, so we represent like nil here and nil here. And in the right, the same, T, 3 and nil. So this is the representation of this tree with the first label of this element here, this node. We call to these elements node of the tree. So nodes. Here we have, in this node, we have a label. Okay. Label will be number 1, or will be a letter, or whatever. Will be a list. We can have a tree of list or whatever element. So this is the representation. The word T, or the letter T, and parentheses, the label, and after that the tree at the left and tree at the right. We use T, but will be possible to do the same with tree. If we write in tree or whatever other word, but is longer because we have to write the T many times. So we use, instead of tree, we write only T. Okay, to do more simple the representation and shorter. So instead write tree, we only write T. Okay.
Okay.
Let's go to PL. Binary trees. Perfect. So now we have the representation and one example of tree. Let's go to implement some predicates. Let's go to find one element in a tree. Find one element. We have element, a tree, and that will be true. It is true if element is included in tree. Okay, so that will be true if the element is inside the tree. Let's go to apply induction here. In this way, in this type of exercises, induction are created not with deleting one element. That usually induction we have usually the first part, if the property have to be true for the n0, and the second part of induction, if the property is true for n minus 1, then will be true for n. Okay, in Prolog, remember on that for n greater than n0, and the property the n n2 is n minus 1, property the n2. Okay, this is the induction in Prolog in this schematic way. What happened with trees? With trees, we don't delete one element. What is the case of, if general case of induction? In case of trees, we will use the left part of the tree. If the left tree and right tree to create induction. We will use left tree and right tree to create induction. So in general, we can say, okay, here in this case of induction, we delete 1, but now we will take the tree of the left and the tree at the right as a way to delete things. So at the end, we have here, okay, if the problem without something, in this case without 1, is true, the full problem will be true. So in case of 3, if the problem of the left and the right is true, if left 3 and right 3 is true, then the full tree is true. Something like that. Okay? If la is true, with true, the full tree is true. Okay? So in this case, we don't delete only 1. We take the solution for the left side of the tree and the right. And if that is true and that is true, what happened with the full tree? Okay? This is the way we will create induction in trees, taking the left and the right side of the tree. Okay, now let's go to find elements in a tree using induction. What will be the easier way to find an element in a tree? What will be the easiest way to find one element in a tree? We have.
And there's only a root?
Yeah, we have the element we want to find, and we have a tree with a label here. The most simple option is if the element is just in the root, in the first element. It's like, okay, we want to find the number 1 in this tree. If the number 1 is in the first element here, it's okay, that is true. This is the N0 case, the most simple case to find one element in a tree, to find just here in the first node. Okay? And this is the way to represent that in Prolog. It's okay, that is true if the element is in the position of the label of the first node of the tree. And doesn't matter, you are at the left and on the right, but that is, the element is here, that is true. Okay? Everyone can see this simple case or not?
Yeah.
Yeah?
See.
Okay, now if not, or what is the option for induction? Let's go to find element in a tree with wherever label, doesn't matter, and left tree and right tree. When it's true, when that is true, if we have 2 trees in the left and the right, how I can create this predicate to find one element in a tree? If I have one element in the left, or one tree in the left and one tree in the right, what I have to do?
We have do we have to take the like
It's like
the command, the T command with the left tree as a root, if this is true, and the right tree as a root, like the.
Which line? You are talking about line 58?
Yeah, you said that both trees have to be true. Like the left tree and the right tree.
I am trying to find this element in the tree. So the first option is I want to find this element. In this case, this more simple case, the element is in the root or in the first node of the tree. And now I have a tree with left and right. Like I have two trees. So I have two options to find this element, or three options. Is in the here, in the label, or is in the left, or is in the right. So I need to write the three cases. I only have three options. I can find the element in the first node is here, or the element is here in the left, or is in the right. So that is true if the element, remember, it's something like is true, A is true if is in the left or is in the right. Remember how we do when we have this type of rules. This is not a horn clauses. This is not a horn clause, but I can find a translation. I can say, okay, that is true if is here or is here. What do we do in this case? Do you remember that? It's like if that is true, A is true is B or C. It's like A is true if B and A is true. See, we create two rules. Do you remember that?
Mm-hmm.
So what we have to do here, okay, that is true, is find the element in the left tree. If that is true, that will be true. If that is true, if the element is in the left, the element is in the tree. And the second part is find element in the tree with whatever label and wherever here and right T, and the same here because we don't use that. That is true if I can find the element in the right tree. This is the three options we have. Or the element is in the first node, is here, line 56, or the element is in the left, or the element is in the right. And there are no more options to find one element in a tree. In the label, in the first node, in the left, or in the right. Okay? Let's go to create something here. Okay, and now I'm gonna give you a trick to create trees in a simple way, because sometimes it will be difficult to write the trees because you have many parentheses, so will be something difficult. So let me give you a trick to create this tree using in Prolog representation. It's like we start with a T, parentheses and dot. Okay? First, we have to represent this element is label number 1 and I have a tree in the left and a tree in the right. I have a tree in the left and a tree in the right. So the tree at the left is number 2 and 2 trees. And here in the second tree I have a level 3 and a 3 and nothing here. I have nothing here in the right, so here I have to write nil. Okay, and here then in this tree with 2 I have 2 trees. I have tree number 4 and nothing more. It's like 4 and nil. Nil is a way to represent. Nil is a way to represent an empty tree. And here the 5, nil and nil. Okay, and this is a way to represent this tree. Can you do the same? Can you create a tree by yourself and represent in Prolog using these techniques? You want to repeat this, the way to create that or not? Hi, good morning.
Yeah, yes.
Do you want to repeat or not?
Now, I don't understand, sorry.
I'm trying to explain the way to write the representation for...
Yeah, I understand how to create this type of tree, yeah.
Okay. Can you do one, create one by yourself and create your own representation? Can you create a new tree and represent by yourself?
Yeah, okay, no problem.
Okay. Oh, I will give you 5 minutes or less, a little bit less. And please create a new tree and try to represent using these techniques. It's like starting with T, parenthesis, parenthesis, dot, and then create a step by step. I give here a label and tree and so on. Okay, create the tree using this technique, because otherwise it will be very difficult and it's possible you forget one parenthesis at the end, or but in this way it will be easier to create the tree. Please create one tree by yourself and represent using this trick. Okay, I will reconnect in 5 minutes.
Okay.
Okay, perfect.
Okay. Okay, you have the result.
Yeah, I do the exercise, but I don't understand how I put on Prolog.
Or you can put in Prolog. Can you share your screen? Is possible? Okay, let's go see. You have to share all your stream. And you have to take this way. Okay, nice. No, okay. Can you put a little bit grade the font and Control ++ to make the font. Okay, nice, perfect. So, I don't know what is a tree. Do you create the representation of this tree or not? You create, I suppose, in a paper or by hand? Can you paint this tree or not? Hi. Okay, nice. Okay, here you have an 8 instead of 3. I don't think so. I don't. Christian, can you hear me?
Sorry, I have the push button for talk. I'm talking with no one.
Okay.
Sorry.
Okay. So I think you have a mistake here because it's not like 3 and 3. You have 3, and in line 8,
Yeah.
you have an 8, not another 3.
I have on the line 8.
Line 8, you put here.
Yeah.
It's not like this. You have to put in the instead of 3 and number 8. Not here. Don't change the tree. Change the this picture of your tree. Line 8, you have an 8 instead a number 3.
A moment. 1, 2, 5, 4. Why it's not correct? Sorry.
Line 8.
Yeah.
You write in the right side of the tree. You write a number 3. Is it an 8? You have to delete the other 8 in number 10. I think that is the representation you have. This is the tree. It's 1 in the left, 2 with 5, 4, and 5 a half a son is number 7, and 3 height 8 and 9, but no more.
Yeah.
Okay?
Yeah, okay. Thanks.
Okay, if you want to use that in Prolog, I'm gonna give you a trick.
Yeah.
Thank you, Christian. I'm gonna give you how you can use this tree for this example. I'm gonna share my screen. I'm gonna share my screen. Now, okay.
This is the code.
Okay. I'm gonna give you a trick. If you want to use this tree, for example, can you see my screen?
Yes.
If you want to use this tree, I'm gonna copy, because this tree is inside a comment. I'm gonna paste here in the code. After that, after the implementation of find, and I'm going to put to create, for example, tree 1 parenthesis, and at the end I'm gonna put another parenthesis. Okay, it's like put all your tree inside this name, tree 1 parenthesis, and all your tree. If you have more trees, for example, I have another one here, this tree, I'm going to do the same. I'm going to copy this line, and here I'm going to write tree 2 and put inside all the tree and a parenthesis at the end. So now we have 2 examples to use for our predicates of binary trees. So I didn't tell you why we call binary trees. We call binary trees because
you have only one left and one right.
Yeah, you have a maximum. You have a maximum two branches. Maximum 2 branches.
Yeah.
You can have 0, 1, or 2, but maximum 2. After that, we will see the generic tree where you can have more branches for each node. But in case of binary tree, we have only 2 branches for each node, a maximum. Okay, so we are ready to check if our predicate works. Let's go to open with Prolog. Let's go to open these binary trees. No, listing tree 1, for example. We have the tree. Let's go to find. This is the predicate. And let's go to check, for example. Let's go to find if the number in tree 1 we have numbers 1, 2, 3, 4, 5. Let's go to find the number 5, for example, inside the. Sorry. First we have to say, okay, tree 1 is a variable t, and now find element 5 in t. This is the way to check our predicates. First part, we unify the variable t with the tree here, And after that, let's go to check if the number 5 is inside the tree T. So, and say, okay, that is true, and give me the solution. That is true when the tree is all that tree. So that is true. Let's go to try to find a number that is not inside the tree. Let's go to find number 6 that is not in the tree. Say that is false. The number 6 is not in the tree. If we check the time, we need to do that. Time. We need only to check 13 evaluations to obtain the result. In case of number 5, we need only 4 terms evaluate to obtain the result. That's algorithm very, very fast to obtain this solution. And if we will have a binary search tree, we will obtain the result faster. You know what is that? Binary search tree. You know what's that? A binary search tree are similar to our binary trees with a special characteristic, like binary search tree. Do you know about that? This type of trees?
Yes. More or less, I think.
Okay.
I heard about it.
Okay, let's go to remember.
Yeah, that left side is like the lower numbers, for example, than the on the right.
Yeah. For example, let's go to type here, number 10. In the left of this type of trees, we will have numbers that are less than the root. So here we will have numbers that are less than 10, and in the right only numbers that are greater than 10. So here we will have, for example, number 5. So in the left we can have only numbers that are less, for example, number 3, and here only numbers that are greater than 5, number 7. But greater than 5, but always less than 10. So here, all numbers here are less than this number. And in the right, we will have, for example, 15. And in the left, I can have, for example, 11. And in the right, I can have 17, something like that. So in the left, always numbers less than this number and the root, and in the right, numbers that are high than the numbers of we have in the right. So, and we can repeat the same structure for each node. Here in this node, the same. In the left, numbers that are less than this number, and the right, numbers that are high. Let's go to represent this tree. Let's go to create this tree. If you can do with me. I'm gonna share this file for you if you want to write inside this file. I'm gonna share here, blah, blah, blah. Okay, so let's go to create the tree. It's like T at the beginning, number 10, and 2 trees, and the left and the right. In the left, number 5 and 2 trees. In the right, number 15 and 2 trees. Okay, and in number 5 we have a 3 nil nil, and in the right 7 nil nil. In the left of 15 we have 11 nil, sorry, nil nil, and in the right 17 nil nil. Okay, let's go to implement a way to find a number in this binary search tree. I'm gonna copy this tree and create a new one. It's like 3 3. Paste and put another parenthesis at the end. So let's go to find in a binary search tree. Let's go to the predicate will be find binary. We have the same one element, and we have tree. It is true if element is inside the, let's go to call this binary search tree, inside the binary search tree PST. Okay, let's go to find this inside this binary tree. So tell me, what is the faster option? To find inside this binary search tree. Find B. Let's go to what is the faster? What is the most simple case? What is the N0 for to find?
Like before, when the element is the root.
Okay, nice. The element is in the root level. Wherever, doesn't matter here, doesn't matter here. Okay, if the element is in the root, the element is inside the tree. Okay, that is true. Okay, other option. We have two options. Find and BST. Tell me, what is the option? I have a tree. I have here an element and a tree, left tree and the right tree. What I have to do here, if the element is not in the root, what I have to do?
You have to check if it's like lower or higher.
Yeah, if the element is less sorry, if element is less than the element that is in the root, if element is less, I'm gonna call that the root. It's better. If element is less than the root, what happened?
We are going into the left tree.
We have to find, there is a tree, the element in the left. Have no sense try to find in the right. Okay, so I can here I have to put that means I don't use the right side of the tree. Perfect. And the other side, other part is find the element in the tree that have a root and left tree and the right tree. What I have to do?
If the elements are higher than root, we going to
If the element is higher, it's way down, the root, the element have to be find the element in the right tree. If that is true, that will be true, and the left side. Okay, this is a modification to find the element in a binary search tree, and now we can check if the result is faster or not. Okay, let's go to check. I'm gonna share this code for you. Okay, let's go to check if that works. And let's make a listing, find in binary search tree. Okay, this is the different implementation with this checking if element is less than the root or element is greater than the root. So fine, let's go to use the binary search tree is the number 3, and this is a tree. We have numbers 10, 5, 15, 3, 7, 11, 17. So I have a tree is a tree, find binary search tree, and the element, for example, 17 in G. Okay, so it is true, and let's go to check the time. The times needed to find this element. Only 6 inferences. Only have to check 6 terms. Let's go to apply the order. The usual find, binary find, is like how many inferences or how many terms have to check. In this case, 11 are more or less the double number of inferences to obtain the result. Okay, so the binary search tree are one of the faster structure to find elements in a huge number of elements. Very common in databases index. If you want to find if an element is inside a database, usually this structure of binary search tree are used to find that. Okay? Do you have any question about that?
No, for me it's okay.
The rest of the people, Gabriela?
Okay.
Gabriela?
Yes, it's okay.
It's okay for you?
Yes.
Mario?
Yes.
Okay, and Jeffrey, that's new for you. Did you understand or not? Hi, Jeffrey, are you there? Okay, probably. And Colleen?
Sí.
Okay, it's okay for you? Okay, now let's go to create a predicate to build a binary tree from a list of elements. Okay, it's like something like in this case not a binary search tree, only a binary tree. Okay, because to create a binary search tree is a little bit more complex. But let's go to at the beginning to create only a binary tree from a list of number. Probably after that let's go to check if the tree we create will be a binary search tree too. But it's like create. We have the beginning a list. And the result, this is the input, and this is the result, input and output, a tree. It is true if tree represent a binary tree with all elements included in list. Okay, did you understand what's that? It's like, for example, here we have create list 1, 2, 3 and 3. The result have to be a tree with all elements like 1, 3, 2, nil, and 3, nil, something like that. Okay?
Yes, okay.
Okay. So let's go to create that using induction. So I have to create what I have to give a solution for the first list. Let's go to remember induction again. Let's go to create a tree for the first or the most little list. What I have to write here?
Empty list.
Yeah.
Empty list, okay. Empty list. What is the result? If we have an empty list, what is the result here?
Empty tree.
Okay, empty tree is nil.
No, nil, yeah.
Okay? An empty tree is nil. So nil is a tree, is a valid tree, binary tree. So create a tree from an empty list is just nil. Okay?
Yeah.
And
Yes.
now okay, let's go to try to create in a classic way. What is the usual way to deal with list? What we usually do here with with list.
Using head and tail.
Yeah, exactly. So we do head and tail, and we ask to the tail, create a tail and a tree. If that is true, what we have here? In Chi. When that is true, what we have in Chi? You only need to read this line to know what you have here when that is true.
3.
Yeah. You have a tree with what? Here, when that is true, valid. We have a valid binary tree. With all elements of the tail. Okay, I'm gonna give you 5 minutes. Try to think what you have to put here to obtain the solution. Okay? Think about what you have to put here to obtain the solution, and we will reconnect it, and we'll reconnect in 5 minutes. Okay? Try to obtain the solution.
Okay.
Okay? We will connect in 5 minutes. Hi, do you have the solution?
No, I don't know. Sorry.
Don't know.
No.
No, me neither. Sorry.
Okay.
I think it's not working.
Jeffrey, are you there? Who want to show their code to try to resolve, or you prefer I show my code directly? Okay, I'm gonna share my screen because you tried something or not? You tried to do something?
Yeah, but
Michael, share your screen, please.
I can, but it's, I think, really false.
Okay. 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 Can you make the font a little bit bigger?
Yep.
Okay. Perfect. Remember, first thing, line 107. Line 107.
Yeah.
Operator is only to do arithmetic operation. So.
Okay. Yeah, this was the only.
Yeah. And T2, you have to write variables in. Okay. Head, create tail.
I tried something different first, like this one, for right tail and left tail, but yeah.
Okay. I think will be better to start with with line 109 and 110.
Yeah, this was my first approach.
Yeah, I think
And
it will be better because here is more complicated. Here you have another. Yeah.
I know.
Yeah, it's more complicated because we have to think in terms of the n-1. In this case, okay, we have a solution for the tail. Please remove this comment here.
Yeah.
Remove that. And you can delete these lines or comment what you prefer. If you want to comment. Okay. Okay, nice. Perfect. So, line 108. Line 108. If that is true, what do we have in RT? Please, and delete that. Delete head, tail, or not. Leave. Okay.
Okay.
Remove that, please. Remove that. Is something similar to this. Okay. And leave the variable this you had before. Exactly.
Yeah.
When that is true, what do you have in RT line 108? What do you have there in RT?
The right tree.
You have a tree, a binary tree, with a valid binary tree with all elements of the tail. No?
Yeah. Yeah.
You only need to put in a correct way the head. Okay, so we can create a new tree? Yeah.
With a head.
Yeah.
And then the right tree.
Yeah. Perfect.
And then any
No.
Only this. Yeah.
No.
Nil. Yeah.
Nil.
So.
Doesn't matter. It's
yeah.
Yeah. That's all.
Okay.
This is a valid tree. Line 108. You have a valid tree here.
Okay.
And you have a valid tree here. That's okay.
Yeah. Sure.
The problem of this representation, if you have all elements in only in left side of the tree. Okay, this is the problem. But you create a valid tree. Please check if that works. Please.
Yeah. Yeah, it works.
Okay.
Should I show you? No, it's okay.
No, we can
so I have a tree with
result, but I can do the same. I can do the same, and try to check for all of you if you want.
Yeah, I only shared my Visual Studio Code.
Okay. I'm gonna
screen with you.
I'm gonna share my screen.
But it's working.
Again, and show you the result, and do exactly the same code you write. It's like, okay, I have the T, and my T is the head here, T and nil. Okay? It's exactly the same you write. The only difference you write
sure.
RT and okay. So let's go to check if that works. Like make here and listing create. Okay. So let's go to create a binary tree with a list 1, 2, 3, 4, 5, for example. Okay, this is a valid tree, but what is the problem of this tree? You have a tree, something like that. Here we create a tree, something like 1, 2, 3, 4, 4 and 5. And this is a very inefficient tree. Like, but at the end you have something like a list.
Mhm.
You have not a. It's called in trees we call the characteristic to have the elements, and in a short number of levels possible is a balance. So balance tree is like is a tree that is something like that. Is have number 1, and here you have number 2, for example, 2 and 3, and number 4 and 5. Okay, this is a balanced tree. That means you have the minimum number of levels in the tree, and the balanced tree say, okay, the difference between left and right as songs deep is maximum of 1. So the difference between for each node for all node 3. So this is a way to represent this idea of balanced tree. That means the difference between the left and the right, and the deep or the number of levels is the maximum of 1. So here, what is the number of levels in the right side, in the left side of the tree? How many levels you have here? 1 and 2. And here, how many levels we have?
1.
Only 1. So 2 minus 1 is 2 minus 1. It's okay. But what is the difference of levels here? What is the level of in the right?
Cool.
How many levels you have in the right?
On the right, 0.
0, and in the left?
5.
1, 2, 3, 4, 5. Okay,
4.
5. So the difference between left and right levels, number of levels, is greater than 1. So this is not a balanced tree, and this is a balanced tree. So let's go to try to create a balanced tree, not only a whatever tree like this one. Let's go to create another predicate for trees. In this case, create number 2 is you have a list and a tree. And that is true. It is true if T is a binary tree with all elements of list. Okay, how we can create a different tree here with trying to make the balance of these two trees. Create 2. First case of induction. What is the result for empty list? What's the result for empty list? If we want to create a tree.
Nil.
Nil. Okay, perfect. Nice. And now, what we are going to do? Let's go to try to divide the list into parts. It's good to try to divide this list into parts with the same number of elements if possible. How we can do that? We have a predicate in Prolog is integer division is like x is 5 div 2 is the integer division, because if we use the usual division we have 2.5, but we want the integer division, we will use the div. Okay, that means if we use this div and the number is number like this, we have exactly 2 equal parts, but if we have number 5, we have a part with 2 elements, another part with 3 elements. Okay, so let's go to use div to obtain x is length. Sorry. So we need first the length of the list is L. Let's go to obtain the middle of side of this, like middle is length div 2. How we can create 2 equal parts? Using append. We can divide the list in 2 equal parts. Using the reverse use of append. Sorry. Do you know how we can create to divide the list into parts with append? What happened if I make something like this one and mid? What we can obtain here in list 1? Okay, I'm gonna write this one, these 2, list. Okay, I'm gonna do this in the different here. Okay. I have length list 1, 2, 3, 4 in length. Okay. Here I have the length of the list. Okay.
Yes, okay.
Yeah.
Okay. Now, give me. I want to the middle point or the middle side of this list is like it is length divided by 2. It's okay. So the middle is 2. Okay. I want to create a list with only 2 this side of mid. I can do with append, a reverse use of append, this one mid. What happened here? Sorry. Append. No, sorry. I make a mistake here. Is use of length. Okay. L1 mid. What happened here with this use of reverse of length? Sorry, make a mistake here. It's length. Not happened here. Length. This is the reverse use of length. It's like length, give me a list with two elements. What happened here? I create a list with two free variables, and when I use that, for example, I use that to with append list 1 and list 2 and list 1, 2, 3, 4. What happened? If I create a list with two elements and after that I use this list to with append.
I think you have two lists, L1 with the first two element and L2 to the last two, no?
Exactly. Sorry. Sorry. L1.
Okay.
Okay. That is exactly what we want. We want to divide the list into two equal parts. In case we have 5 elements, at least the first list will have only two, and the second part will have 3. But this is the only different. Only one element at maximum if we use a div. Okay? Do you take it, the idea?
Okay.
Take the idea? The idea is first, reverse use of length to create. So first part is okay. I obtain the length of the initial list. This is our first list, 1, 5, for example. I have the length here. This is the first part. I obtain the length. Second part, I obtain the middle point is length divided by 2. Sorry. Length divided by 2. Okay. I have the middle length of the list, initial list. Okay. Second part or the third part. Let's go to use the reverse use of length. Length L1 middle. I obtain a list with the only 2 elements, and the last is append. I can do that another way. Sorry. Okay, I'm gonna show you here. So first, reverse. Normal use of list. I have the list and obtain the size of the list. Second part, I obtain the middle point of the list with div. Reverse use of
sorry, Prof, but mid is length.
Mid is length divided by 2. Sorry, length.
Not length.
Length.
With the okay.
Okay.
Yes.
And now reverse use of append and obtain two parts with the same size or the maximum 1 element of difference. Okay. In L1 and L2. It's okay?
Yes.
Yeah.
Now create L1 3.1 and create L2 3.2. if that is true, what I have here in T1 and T2? Sorry. I have to do one thing here. Head bar list. It's better. Okay. If that is true, what I have here? What I have here in T1, if that is true, if that create a binary tree.
I have a binary tree with all elements of list 1.
Perfect. It's a binary tree. It's a binary tree with all elements of L1. And what I have here?
The same with from list 2.
Okay. What I have to do with T1 and T2 to obtain the full tree?
Creating a new tree.
Yeah. With what?
With the head T1 and T2.
Yeah. Okay, let's go to check. Create two. It's very important to do that. I'm gonna share this code for you. I'm gonna share this code. Okay. Now, make listing create two. So we have first line, empty list with nil, perfect. Second part, here the trick is it's take the head, because in this way is easy because we have the left part and right part and only need to put the head here. It's better than before putting only the list. Okay, I take the first one and the rest, and I'm going to divide the rest by 2 and create 2 equal lists, more or less, only one different, and obtain the 2 trees, and we only need to put all together here. It's okay. Okay, let's go to check. Create 2 list 1 2 3 4 5 6 and 3. The result is now we have a binary tree balance it. It's not like the other way that all the elements are in one branch. Now we have elements distributed equally in 2 branches. Now, for example,
and you can have a tree and convert in a list too.
Sorry?
And if you put a tree,
yeah,
you obtain a list too, no?
I'm not sure. I'm not sure. Let's go to check. Create 2. This T. Yeah. Yeah,
Okay. Thanks.
I think so. I'm not sure. 3, 1, nil, nil. Yeah. And 3, 2. Oh. It doesn't work. So it's not. I think it's not a good example of reversible predicate. It's not.
Okay,
It's not
thanks.
working so good. So it works sometimes, but not always, because probably they have to
Complete
they have to create many trees trying to find the
Yeah.
solution, so will be hard. But the normal way is like this. I have the list, I have a variable, and I can obtain a tree. This is a binary search tree or not? What do you think?
This, yes. No.
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 What I have
No.
to do to create a binary search tree? What do you think? We have to modify here to obtain a binary search.
The first element, it will be the meat.
Yeah, exactly. So, what we can do that? This what have to be the difference here? Like, I'm gonna create 3. I'm gonna leave this is working. Let's go to create a new one. Create 3, 3, and 3. Okay, what you have to do here? I think first remove that, and the head is not here. And what
The head.
we need the middle point. The middle point is the first one of the list 2. It's
Yes.
like here. Or head, not head. Let's go to call this number P. It's like a pivot or a middle of M. If I put here the M, I think that's all. Okay?
Okay.
I think that's all. Let's go to check if that works. Make a listing, create 3. Okay. And let's go to create 3. Okay, now we have 4 in the root. To the left, this is the 3 to the left until here. This is the number to the left. 2, and to the left 1, and to the right 3, and to the right 6, left 5. This is a binary search tree. We can check like find binary search tree, like trying to find number 6 in G. It's true. In the other case, in case of created 2, probably it didn't find it because it's not in a good order. Oh, in this case, yes, but for example, 1, if I try to find number 2, probably it doesn't find. False. Because the tree starts with number 1, and to the left have number 2. This is not fulfill the rule of binary search tree. Okay? Any question?
Yes. No, for me it's okay.
Okay. So now you have a way to create a binary search tree from a list of elements. You need elements in right order. That is important because otherwise it doesn't work. You need you can sort the list before to create this tree. Okay, this is only restriction for this create a binary search tree.
Okay.
So we can change the name. We can change the name here, and let's go create binary search tree. Okay. Any question or?
It's okay for me.
It's okay. What about the rest of the people? Everyone understood more or less about that or not?
Yeah.
Yeah?
Okay.
Okay, nice. So perfect. You can play. Please try to play a little bit. Create your own trees. Try to find elements there. And you can do at the same time, try to check the efficiency of the search. The time is like make listing, create binary search tree, create binary search tree 1 2 3 4 5 6 like 6 sorry 6 the tree and find binary search tree number 6 for example in tree, and you can play trying to obtain the time you need to do that, the number of inferences. In this case only 2. You need to check only 2. If you create more 7 8 9 10 11 12, you can see that the time you need to obtain the result is always very fast, only 8 inferences, and faster than if you use only the binary find, not a binary search tree or usual find. You need almost the double of inferences to obtain the result. Okay? Nice. See you next day.
Okay.
Okay?
See you.
Okay. Bye. See you next day.
Bye.
Thank you.
Bye.